Hello and welcome to a very different vibe for this channel. I'm the boy who lived twice, and today we're going to be talking about the single coolest thing I ever learned and proved in a math class. The fact is brought to you by Professor Birgit Spey, who taught the Introduction to Number Theory course I took at Cornell University. The proof, however, was left as a homework assignment. There are other ways to do this, but I like mine. Let's get into it. So, the coolest proof in all of number theory is that for any prime number p where p is greater than 3, so 5, 7, 11, 13, 17, 19, on and on and on, occurring infinitely many times, although increasingly farther apart, for all of numbers, p squared minus 1 is congruent to 0 mod 24, meaning that it is a multiple of 24. If you divide by 24, you get 0 remainder. You can check this for any cases you want, but as we are about to demonstrate, this is analytically true, which is super cool. So, how are we going to start this proof? Well, we're dealing with a modulus anyway, so let's start with p is necessarily congruent to 1 or 2 mod 3, meaning that for any prime number p greater than 3, it's either 1 or 2 more than a multiple of 3. Because it can't be a multiple of 3, being prime and greater than 3, those are the only two options. All numbers are either 1 or 2 more than a multiple of 3 unless they are a multiple of 3. So we then square both sides and we get p squared congruent to 1 mod 3 because 1 squared is 1 and 2 squared is 4, but 4 is 1 mod 3 because it's 1 more than a multiple of 3, 3. We then have that p squared minus 1 is congruent to 0 mod 3, meaning that for our number, p squared minus 1, is a multiple of 3. Hold on to that, we'll come back in a minute. Next, we're going to deal with the fact that p is odd. For any prime greater than 3, p must be odd. The only even prime is 2, and 2 is less than 3. So we can write p as 2n plus 1 for some natural number n. We then square both sides, and we get p squared equals 4n squared plus 4n plus 1. FOIL, yay. We then can subtract 1 and factor, and we get that p squared minus 1 equals 4 times n plus 1. Now for natural number n, either n or n plus 1 must be even. Two consecutive numbers, one must be even. So we can take a 2 out of that, take the 2 outside, multiply by the 4, and we get p squared minus 1 equals 8 times n plus 1 divided by 2. N times n plus 1 divided by 2 must be a natural number because we know that one of them is even. So we get p squared minus 1 is congruent to 0 mod 8. Our number is a multiple of 8. So now, for our conclusion. We know that our number is a multiple of 3 and a multiple of 8. It therefore must be a multiple of their product 24 because 3 and 8 are co-prime, meaning they do not share any prime factors, they don't share divisors, they are in terms of each other prime numbers. 3 is actually prime, but 8's only prime factor is 2, and 2 and 3 don't divide. So we have our p squared minus 1 is congruent to 0 mod 24. For anybody who knows stuff about prime numbers, this is super weird. Primes do not like patterns. They don't fall into patterns nicely. We can very easily prove and demonstrate analytically that there are infinitely many primes, but it is really hard to tell how often they're going to occur. It's been conclusively demonstrated that the occurrence of primes is random, but they all fit this neat little pattern. And that is super cool. QED. If you enjoyed this, please like and subscribe, and I'll see you next time. Bye.